Well, good day, students. Here we are with our second video, and as you can see, I'm going to use PowerPoint for this presentation. The marker board works great for some things, but sometimes my writing gets a little sloppy and sometimes it's a little bit inefficient. So we've worked a correlation problem in class, and so I'm going to work another one here from scratch. And what I want you to do is follow along and use these steps and these procedures to work the problem that I've placed online. So you'll have a new problem online, print that out, and then work through these exact same steps, and then turn in your work on Tuesday. So you can see here the question is, generally speaking, is anxiety related to depression? Now, psychologists often ask this question as, is there a linear association between anxiety and depression? Now, given what we've also talked about in class, we know to add the words in the population if the psychologist is looking for statistical significance using NHST. And as you know, that's pretty much the name of the game, unfortunately, today, is looking for statistical significance. So, sure enough, the question is there a linear association between anxiety and depression in the population? So we're going to make that inference from our sample to the population parameter. Now, suppose a psychologist assesses anxiety and depression using well-known questionnaires, and these questionnaires yield scores ranging from 0 to 63, and high scores indicate higher levels of anxiety or higher levels of depression. So we have 8 individuals here. The first person scores a 5 on anxiety, a 6 on depression. Second person scores a 7 on anxiety, 9 on depression, and so forth. Now, given what the researcher knows about anxiety and depression, and this makes sense to you, I'm sure, in your common experience, she expects a positive and statistically significant correlation between the two variables. So high levels of anxiety ought to go with high levels of depression, and low levels of anxiety should go with low levels of depression when you look across these 8 individuals. So let's compute the correlation test and test it for statistical significance, and we're going to use an alpha level of 0.5. I will provide this for you almost every time. In the general research out there, this is what most folks use, a p-value of 0.05. Sometimes 0.1, sometimes 0.1, but surely 0.05 is the most popular value. And we could talk more about this in class later. So we can begin by writing our hypotheses. So we know we're computing a Pearson's correlation coefficient, and our hypotheses are then the null hypothesis is the population correlation is 0. The alternative is it's greater than 0 or less than 0. And this is what we're predicting here. The population correlation should be positive. Again, high anxiety with high depression and low anxiety with low depression. We then set up our sampling distribution of the correlation coefficient, and we'll have our alpha 0.5, so we'll have 2.5% on the bottom, 2.5% on the top. So there's our alpha, our p critical value as it's also known as. Then the sample size here is 8, and then the degrees of freedom are n-2. Let's go to the correlation handout and remind ourselves where we got that degrees of freedom value from. So here's the handout. There are the hypotheses. There's the sampling distribution, and then here we see the degrees of freedom are equal to n-2. Now, by the way, let me mention this quickly. As the sample size changes, so here we're using 8 for our problem. What if it were 30? So we're sampling 30 people, and we're doing that over and over again. What does the sampling distribution of the correlation coefficient look like? Does it look exactly like this? Well, it will look like that in general. It will be mesocurtic, but it will change its shape. So the sampling distribution of the correlation will change its shape depending upon your sample size. So there are potentially then an infinite number of these sampling distributions of the correlation coefficient. So the degrees of freedom helps you to basically jump into the right sampling distribution. So then you can cut off the rejection region. So just think of the degrees of freedom in that way. It is a number you can use to jump into the correct sampling distribution so you can cut off your rejection region, look up your values, and test for statistical significance. So let's switch back to PowerPoint now and carry on. So here we have degrees of freedom n-2 again, and that's equal to 6. And we go to our correlation table now so we can get the values that chop off 2.5% on either side. So here's the table on the left, the correlation coefficient. We're using an alpha of 0.5, so we'll use this column here. And the degrees of freedom are equal to 6, and so we can see the 0.707 there. I don't think I can highlight it. Well, maybe I can. Nope, doesn't look like it. So we see the 0.707 there. Okay, there you go. So there's the 0.707 value. So I've already got that here, negative 707 on the left, positive on the right. Again, this is distribution centered at 0. And so that is our critical value for determining statistical significance. So now let's begin plugging and chugging through. So we have our data here again, and the first thing I need to do is get the means and standard deviations for the two variables. So you can plug these data into SPSS, plug them into Excel, plug them into your calculators, and get these values. There are online calculators you can use. I'll show you one here quickly. So here's an online calculator, and you can see I've put in the data for the depression scores, I believe, and select calculate, and you get the mean of 8.63 and standard deviation of 2.39. So you can just copy those over. So there they are, 8.63, 2.39. So now that you have those values calculated, you can get your deviation scores. So here we have x minus x bar, so 5 minus 8 is negative 3, 7 minus 8 is negative 1, and so forth. And then here, 6 minus 8.63 is negative 2.63, 9 minus 8.63 is 0.37, and so forth. Again, this column, these values should sum up to 0 within rounding. These should sum up to 0 within rounding as well. Now we get the cross products. So we take negative 3 times negative 2.63, and that gives us 7.89. Negative 1 times 0.37, that gives us negative 0.37, and so forth. We add these up here, capital sigma equals sum, and we get exactly 20. So that is the sum of the product of the deviations about the respective means. Now we go to our Pearson correlation handout again, and we see the formulas here. So I'll get the covariance first. I need the sum of those products of the deviations, which we just computed. Take that divided by n minus 1. So we'll put the formulas here. So there it is. 20 divided by 7 is 2.86. Then we go back to the sheet, get the correlation formula, which is the covariance of the product of the standard deviations. Again, we have the standard deviations already computed out, so I plug and chug through there, and I get 0.53, so that is my correlation coefficient. Here's the sampling distribution with the critical values. We can see here that negative 0.53 is not in the rejection region, and so we fail to reject the null hypothesis. That is our conclusion here. Now what you're going to read in a published paper is the results are not statistically significant. That correlation is not statistically significant. And again, that is equivalent to failing to reject the null. So our conclusion then is that the population correlation is 0. So based on this correlation we talked about in class, when we run through this NHST, we're basically trying to figure out, is this thing weird enough to reject the null hypothesis? And although 0.53 seems like a decent sized correlation, it's not weird enough to reject the null hypothesis, which again is assumed to be true. So we conclude then that the population correlation is 0. I can't rule out that assumption. And this is not what we expected. We expected a nice positive and statistically significant correlation. Now I'd also like you to write your results like this. It appears that, contrary to expectation, the population correlation between anxiety and depression is equal to 0. In other words, there appears to be no linear association between the two variables in the population. You're not going to see this kind of write-up, likely, in a published paper. But I want you to do it in this class because it reminds us of a couple of things. First and foremost, what are we doing here when we're testing for statistical significance? We're trying to make a statement about a population parameter. So you read this, it appears that, contrary to expectation, the population correlation between anxiety and depression is equal to 0. So we're making a conclusion about a population value. And we also hedge it, don't we? It appears that. Why do we do that? Because we know this is not the population correlation coefficient. We don't have the population, so we have to hedge it. The population correlation could in fact be a nice positive number. It might even be 0.53. But we can't make that conclusion because this is not weird enough in the sampling game, and so we have to hedge it and say it appears that, contrary to expectation, the population correlation is 0. So go ahead and write your results up like this. So we'll remind ourselves we're trying to make an inference to a population value, and it's an uncertain sort of inference. We are going from sample data to the population. Now lastly, we didn't talk about this in class, but you can also get p observed. Now p observed tells you the probability of, in this case, of getting 0.53 or more or negative 0.53 or less. So if I were to shade in the distribution that way and then shade it in that way, what would that total area be? Well, it turns out it's 0.18, which is a lot bigger than the 0.5. So if I shaded it in from here to there and from this point down, it's way too much. I should have been down in this area here or here, which is only 5%. So you can see here when using SPSS, you'll compare this value to p critical, 0.5, and if p obs is less than p crit, then you have a statistically significant result. Clearly 1.8 is not less than or equal to 0.05. Now I'll show you quickly, you can find these calculators online as well. So let's see where I got that 0.18. Again, I could get it from SPSS, but there are other places you can get this computed as well. So let's switch over to the internet. And so you see here is one critical calculator you can find out there. So the correlation was 0.53, and we had 8 individuals. We'll go with the 0.05 level, hit calculate, and there you have it. The p-value is 0.176664, so 0.18. So this is a place you can go if you want to get the p observed for finding a correlation of 0.53 or greater, again on either side of the distribution. So let's go back to the PowerPoint. So now you know where I got that 0.18 from. Again, if you enter your data in SPSS, you'll get the p observed as well, and it's bigger than 0.5, not less than or equal to. So again, it's another way of saying the results are not statistically significant. Now we move on to effect size. Here, RXY, to me and to you, I'm sure it seems like a medium effect. And R squared is a large effect using Cohen's convention, so that's even more impressive if we buy into Cohen's conventions. However, we failed to reject the null, so we concluded, though, that the population correlation is 0. So you can think of it like this. How close did this come to 0? It doesn't seem that close, but it's close enough to where I cannot rule out a population correlation of 0. This will make more sense as we look at the confidence interval. So let's do that now. Confidence interval. We're going to build it around the population R. So it's a 95% confidence interval because we used alpha 0.5. So there is the equation off of the correlation handout. You can see I've plugged in some of the numbers here. R prime 0.59, I'll show you where we got that in a moment. The Z crit, I've talked about that a little in class. If you want me to explain that again, we can, but right now just always use the 1.96. And then the 0.45, I got that by taking 1 divided by 8 minus 3, or 5. So 1/5, take the square root of 1/5, and that's 0.45. So where did I get the 0.59 here? Again, that's R prime. So we go to the Fisher R to Z table. And so here is the table that is on the back side of the correlation table. And we found a correlation, observed correlation of 0.53. So we scroll down until we find that. And here it is, 0.53. And the R prime value then is 0.59. So again, I'm looking down the R column until I find the value I'm looking for within rounding, 0.53, and then I read off the R prime value, which is 0.59. So here is the 0.59 then. So I plug and chug through this, or calculate through it, to get 0.59 plus or minus 0.88. That then gives me negative 0.29 around the population R prime here, up to 1.47. So notice this is around R prime, which is a z-score. I want to back convert it now to a correlation coefficient. These are z-scores here. I want to convert those back to correlations. So I go back to my Fisher's R to Z transform table, and I'm going to look up 0.29 and 1.47. Now I'm looking down the R prime column for 0.29. Here it is, within rounding, 288. And so we'll read off now the R value, the correlation, 0.28. And then what was the other one we were looking for? 1.47. Let's go back and look real quick. So here's the 0.28 that I put in there. Keep the negative sign on it. And then 1.47. So now we go down the R prime column looking for 1.47. And here's 1.472, and that gives me an R of 0.90. So here is the 0.90. So this then is our 95% confidence interval around the population R. And now notice this is very, very wide. And indeed, that would be our conclusion here for this confidence interval, that it's imprecise. It goes all the way from negative 0.28 all the way up to 0.9. So anxiety and depression in the population might be negatively correlated slightly, or they might be almost perfectly correlated. So not any precision here at all in estimating that population parameter. And that then helps you to understand that, okay, that's why the 0.53 looks nice, and even squared you get 0.28, but we only had a sample size of 8. And I could not really zero in on where I think that population R is. It could be as high as 9, or it could be 0, or it could be negative 0.28. So I cannot reject the null hypothesis. The 0.53 is simply not weird enough with a sample size of only 8. So you can see that I did not reject the null here because the population correlation could in fact be 0, which is included in here, negative 2.8 up to 0.9. And again, this is a very imprecise estimate of that population parameter. So for this problem, the results were not statistically significant. The effect size suggests there might be something out there in the population, but our sample size is simply too small, and we don't have a precise estimate of that population correlation then. So we'll have to accept the assumption that the null is true, that anxiety and depression are not correlated in the population. Alright, so work through these steps with the new problem that's posted online and turn that in for your homework assignment on Tuesday.